Welcome, everyone. Thank you for joining again. This is our seminar series, CDY Seminar series, and the speaker today is Qiang Yuan. The title of his talk is Measurements and Implications of Ultra-High Energy Diffuse Gamma Ray Emission from the Galactic Plane. Qiang is at the Purple Mountain Observatory, and his PhD was in particle physics from the Institute of High Energy Physics, Chinese Academy of Sciences. The topic of his thesis was several aspects of indirect detection of dark matter. He's a professor at the Purple Mountain Observatory. He's been a postdoctoral research associate at the University of Astronomy and University of Massachusetts, Amherst. He was a visiting scholar at Keike, Japan, a research faculty at the Institute of High Energy Physics and Chinese Academy of Sciences, a visiting scholar at the University of Nevada, Las Vegas. And his interest is very broad. He works on particle astrophysics, particular focus on indirect detection of dark matter, origin of cosmic rays. He is a member of the dark matter of DAMPI and the first astronomical project of China since 2016, and he's also a member of LASO. So let's just get started. Thank you again, Qiang, for giving us this seminar, and really looking forward to some energetic discussions. Okay, please get started. And
okay. Thank you, Rashmi. Thanks for the invitation and also for this introduction. Okay, so here is just a very brief introduction about the cosmic rays and the related gamma ray emission. For this talk actually focus on this galactic part of the cosmic rays. So basically we have many sources in the Milky Way, and those sources will accelerate cosmic ray particles. Those particles will then propagate in the Milky Way with a quite complicated way. Actually, the main property is to diffuse in the random magnetic field, and it will have energy losses due to different kind of processes, and also may be reaccelerated by some MHD waves, may show some convection propagation. And those interactions will also produce like secondary particles and secondary emission. So this is after all this kind of complicated process, we detect those particles in the neighborhood inside the solar system, and those particles may also be modulated by the heliosphere, and will show some this so-called solar modulation effect. Those mainly affect the low energy behavior particles, and we also detected those multi-wavelength emission from like radio to X-ray to even to gamma rays. So this is the general picture of cosmic rays. And for the diffuse gamma rays, it's expected April to be produced by cosmic ray interaction during the propagation. So we thus use those diffuse gamma rays to probe the propagation and the interaction of cosmic rays. So in general, we have like three processes to produce this diffuse gamma rays. So one is this hadronic process, like this nuclei will interact with interstellar medium and produce neutral pions. Those pions will decay to photons, and it will produce diffuse gamma rays. So this component is highly related with the gas distribution in the Milky Way. So it will show this very clear disk-like morphology. And the other two components are related with the electronic part of the cosmic rays. So these electrons and also positrons will interact with the interstellar medium to produce with this Bremsstrahlung process to produce gamma ray emission. So this component again is related with the gas distribution. And the other component is the inverse Compton process of electrons and positrons in the interstellar radiation field. So this the morphology of this component seems somehow different from this previous two, because this component is more related with the radiation field distribution in the Milky Way. So it will show somehow the different morphology. Beyond those standard processes, we perhaps can have this exotic contribution of this diffuse gamma rays, like the dark matter annihilation or decay. So that is actually is very still very interesting, but is beyond today's topic. So the observations of diffuse gamma rays from the space emission, we have recently we have quite good measurement of the diffuse gamma ray emission. So this older one, older experiments like from the OSO 3 emission. Just observed some several hundred gamma ray events, and then the COSB emission actually can measure this kind of disk of this bright this gamma ray emission, which is mainly from this pion decay of this hadronic interaction. And IGRIT gave the even better measurement of this all-sky diffuse emission. And currently we have Fermi, which is very nice to cover a very wide energy range from like 100 MeV to several hundred GeV energies, and has a very good source subtraction and a very good and morphology measurement of this all-sky diffuse emission. However, if we want to measure this diffuse emission in even higher energy ranges, we currently can only use this ground-based experiments. So in the very high energy range, we have this diffuse measurement by several experiments. For example, this is some old measurement by a Milagro experiment, and shows that measured some emission in the galactic plane at energies around 10 TeV energies, and found some interesting excesses, for example, in this Cygnus region. At the time of Milagro, I think the sensitivity of the gamma ray emission is limited, and the resolved very few sources. So the source subtraction may be limited, and those measurements may contain both the information from the diffuse emission and from some unresolved sources at that time. So HASS is a Cherenkov telescope, has so the field of view of HASS like experiment is somehow small. So to measure this large scale diffuse emission is a little bit challenging, but they still make this attempt to measure the diffuse emission in some regions around the galactic plane. And this results shows that this is the highest results, and they say that longitudinal and latitudinal profiles of the observed gamma rays show characteristic excess emission not attributed to low gamma ray sources. So these measurements again. I think it may also contain part of this source contribution, but there is also they may also measure this truly diffuse component of the emission. So I think in this plot, so this lines may show this prediction from this cosmic ray interaction of this diffuse emission by some specific model, and the measurements show that there is some excess on top of the model prediction. And the ARGO measured the diffuse emission again in the TeV energy range. So in the inner galaxy range, the algo has some successful detection, and in the outer plane, just some limits were given. T-beta AS gamma recently, actually in 2021, like a few years ago, measured for the first time the diffuse emission above 100 TeV, from 100 TeV to 1 PeV. And they also found that there is excess compared with this conventional model prediction. However, there is perhaps one issue for the AS gamma result is that they actually they subtract the source subtraction radius is 0.5 degree. And we know that this kind of source subtraction may be too small according to this, for example, the Hawk results and also the LASSO results. We found that actually quite a number of sources have extensions larger than this value. And so for this kind of source subtraction, maybe this result is again contaminated by this source emission. And this is very recently by Hawk measured this diffuse emission in a region with longitude from this region and latitude 2 degrees or 5 degrees around the galactic plane. So this the Hawk results shows that here is the from their abstract. It shows that the spectrum is comparable with the spectrum, the emission arising from a cosmic ray population with an index similar to that of the observed cosmic rays. When comparing the dragon-based model, so this is some kind of a benchmark model for diffuse emission, the Hawk diffuse flux is higher by about a factor of 2. The unresolved sources such as pulsar wind, nebula, and some halos could explain this excess. So all this kind of observation actually shows that at the high energy region, very high energy to ultra high energy region, so the measured diffuse gamma rays seems is not easy to be just simply explained with this standard cosmic ray model. So there could be something else there. So here it shows a summary of this wideband diffuse emission measurements. At a low energy band, those measurements are from this space satellite, so it looks good. However, above 1 TeV, we see that those measurements are actually quite limited. The data points are sparse, and also these uncertainties are large, and we also see some kind of gaps in this for the energy coverage. And for this outer galactic region, we found only upper limits in this region. So there is no positive detection in this sky region. And this box shows the energy coverage of LASSO. So we see that LASSO actually has a very good potential to measure the diffuse emission in this energy range, which is expected to be very useful, very interesting in understanding this cosmic ray interaction in this energy range. So here is some brief introduction about LASSO. So this is the layout of the LASSO detector. We have three detector arrays. So this is largest one is called this KM2A. It's a kilometer square array. It's made up of 5,000 electron detectors. So this is 1 meter each, and the spacing is 15 meters. And under those electromagnetic detectors, we have more than 1,000 muon detectors. So this is the muon detector basically is to distinguish this electromagnetic showers from those hadronic showers, and which can be very helpful to identify the gamma rays from this high cosmic ray background. In the center of this array, we have a so-called water Cherenkov detector array. So this is very much like a hawk, but with an area is several times bigger than hawk. And we also have 18 Cherenkov telescopes just around this water pool. So this Cherenkov telescopes basically to measure the longitudinal distribution of a shower, and which is very useful to distinguish different particle species, like to separate protons, helium, medium mass nuclei, or heavy nuclei. This would be useful to use this Cherenkov detector. This is a large area and a hybrid detection technique. So we use different kinds of detection technique, can make a large or powerful facility for cosmic rays and gamma ray observation in a wide energy range. So for example, this is an illustration of how we use this muon detectors to do this gamma ray and cosmic ray discrimination. This is a simulation. And so this x-axis is the energy of a shower, and this y-axis is just this simple quantity. Basically, is the number of muons divided by the ratio of muon to electromagnetic particles. So use this simple variable, the so-called R variable, we can have a very good distinguish between this protons and gamma rays. So we see that for protons, basically we have more muons. So this number is bigger, and for gamma rays, the number of muons is much less, much smaller. So we can just use a cut of this R value to reject most of these protons and keep the good fraction of gamma rays. So this plot shows this cut efficiency for cosmic rays and also for gamma rays. For example, for this red showed for the efficiency for gamma rays, we can keep an efficiency like gamma ray efficiency from 90% to 60% to high value, and we suppress the cosmic ray background to a quite low level. For example, at this highest energy range in the PV energy range, the survival fraction of this cosmic rays is like smaller than 10 to minus 5. So in this energy range, this cosmic background is suppressed to a very low level. And this is a background estimate. We mask the galactic plane and also this lone sources and use the residual sky to estimate the background. Use a so-called direct integral method. So this is basically to assume that the spatial distribution of events in the detector coordinate is stable in a reasonable short time beam. So we use these events observed like from sometime earlier and sometime later to estimate the background. To observe the diffuse emission, we also need to subtract the sources. So this is shows actually this is from the first catalog of LASSO. So from the galactic plane, we see that there are quite a number of sources. I think in this plot there are more than 50 or 60 number of sources there. So if we want to measure the diffuse emission, so we need to subtract the sources. So in this analysis, we just choose some mask radius. This mask radius is defined by this, for example, this is the PSF convert with the extension of the source, and we have some number n to mask. In this analysis, we choose n like 2.5. That means 2.5 times bigger than this source extension. And this is the mask catalog. Based on the Chem2A catalog, we also mask the regions where there is a source in the TeV cut. There are some sources that are overlapping. They have the same positions. So in that case, we use the Chem2A parameters to do this source mask. So after that, this is our region of interest after the source mask. So in the inner region, so we actually mask quite a number of sources, regions. In the outer region, the sky is kept reasonable large portion. And we found that even after the source mask, we found a significant emission in this region. In the inner galaxy, this significance is nearly 30 sigma. And in the outer galaxy, we have 13 sigma detection significance for this so-called diffuse emission. And this shows the spectrum in this two region. So this left one is for this inner region, and this is for the outer region. For both region, we found that the spectrum is follows a power law spectrum. And the index is similar, it's -3. And so it's interesting that for this outer plane, we first have this this measurement with relatively high significance. And we also can measure the spatial distribution. This is the longitude and the latitude profiles. The left panel shows this longitude distribution of the emission, and the curve in this plot is the gas distribution according to this Planck opacity and derived gas distribution. So it seems that this emission, this diffuse emission, is not just follow the gas distribution, but it shows like some clustering of the emission. In some regions, the emission is high, but in some regions is somehow low. And the latitude distribution is similar to this gas distribution. So yeah, in the low energy region, looks like this. In the high energy region, I think the same conclusion is again. And also we have the other way to characterize the spatial distribution. We can obtain the angular spectrum of the emission. This black and shaded band shows this the angular power spectrum of the data, and this band shows the statistical uncertainty. This purple line shows the angular power spectrum of the gas distribution. So we see that at this low L range, so basically this is a relatively large spatial scale. At this large spatial scale, we see some kind of deviation of the data from the gas, the prediction of the gas distribution. So I think this is somehow is consistent with this plot. The longitude distribution plot shows. So at some particular angular scale, the data and the gas, their spatial distribution shows some deviation. We then compared the last data with a toy model prediction. So how this model is done? So basically, we have this local measured cosmic reflex this panel is for protons and this panel is for helium. There are some uncertainties, particularly at this high energy Li region. So we use some range to characterize their uncertainties at this high energy range. And we we use this local measured cosmic ray flux and times the gas column density. So let's see the line of sight integration of this gas distribution, and again convolved with the this interaction cross section, and we can get the predicted gamma ray flux. So that's showed by this gray band. So so basically, I think this is assumed that the cosmic ray distribution in the Milky Way is uniform everywhere. And for this case, we can predict that the gamma ray flux is something like this. So the measured flux is we can see that is higher than the this toy model prediction. In this inner region, if we multiply a factor of 3 of the toy model prediction, so that it can roughly consistent with the data. And in the outer region, this is if we multiply a factor of 2, it may be consistent with the measurements. So I think this conclusion is somehow consistent with previously other experiments show that, like a Hawk and also AS gamma and some other experiments, they also show some kind of excess compared with the model prediction. And we also note that the spectra are different from the prediction. So from the model prediction, I think in this part, the spectrum is something like 2.7, something like that. This is due to the cosmic ray spectrum slope. And in this part, this high energy part, there are several effects here. So one is we enter the Li region of the cosmic rays. So this is it will result in a suppression of the flux at a high energy range. And the other effect is that in this energy range, this gamma absorption actually is becomes important in this region. So it will also result in a suppression of the flux. So this spectrum looks like a curved shape, like this one. This is from the prediction. But the observation shows that it's something like a E2-3 power law distribution. So it's maybe different from the prediction. So we found that this fitting p-values, if we use this model predicted spectrum shape to fit the data, we get this p-values like 10⁻⁴ to 10⁻² in this inner region. So it shows that the spectrum is not very consistent as predicted. So this slide shows a so-called toy model. So in this slide, we show some kind of more physical model based on a Galactic computation. So again, we tune the Galactic model parameters to fit the local observed cosmic rays in a wide energy range, like from this MeV to this PeV energies, protons, helium, and we also include the leptons in the cosmic rays, the positron flux, and the electron plus the positron flux. And then we calculate the predicted diffuse gamma ray emission, including all those components from the pion decay, from the Bremsstrahlung, from the inverse Compton components. And the results looks like this black curve, solid black curve in this panel. So we found that again this model cannot simply account for this data from the Fermi to this Lasso observation. And particularly interesting, we found that the axis is mainly in this medium energy range, like from 10 GeV to 10 TeV energy range. So there is excess of the data compared with the model prediction. So does that means there is some kind of unresolved source population in this energy range? So here we just yes.
Just please go ahead. Please go ahead.
Okay. So here we just show to add empirical form of this. It's a power law plus an exponential cutoff form to represent some kind of unknown source population, and we found that it can give a very good match with this data in the in both regions, in the inner region, in the outer region, so in a very wide energy band. If we add this this component, is shown by this green curve, so this data can be nicely reproduced. And so how to quantify this unresolved source contribution? Yeah, because we have observed source catalogs. So so for example, so this is shows this the left panel shows the observed flux distribution of the sources. So if the source flux is high, we just see this kind of intrinsic source distribution. This is something like a luminosity function. And if the flux becomes lower and lower, the detection efficiency becomes smaller, and to some threshold of the flux, we cannot detect those sources anymore. So this this detected number just quickly dropped. So this is what we may observed from the observation. However, intrinsically, this source distribution may look like this way, just like this black line shows the black line distribution. So there is quite some contribution which we may not detected due to the sensitivity of detector. So we may just quantify this part from the observed sources to see how such kind of such unresolved contribution, how large this contribution is in the diffuse emission. So here we do this kind of attempt to based on the first Lasso catalog and use long parametric method, the so-called Lindenbayer method. So here I do not introduce the much detail about this method, but basically it's just to try to extract this intrinsic luminosity function based on the observed source parameters. And for example, here shows this this is the photon index and also the flux of the detected sources, and this dashed line shows this basically the detection threshold of the instrument. So in this part, the source can be detected, but in this part, it's the detection efficiency becomes lower, and it's not and the sources in this region are not completely detected. So we can derive this. So this is a cumulative flux distribution of sources, and the blue shows the observed one. and the red shows the derived the intrinsic one. So it shows that at this low flux range, indeed we have some sources are missed by the detector. So we can estimate the fraction of this emission to this total diffuse emission, which is shown in these panels. So this band shows the expectation for this unresolved contribution according to the WCDA catalog. And this green shows the expectation based on this KM2A catalog. So if we add this contribution to this gray band is the expectation from the cosmic ray interaction. We add this component to this gray one and get this this total emission is shown by this by this band, this pink band. So for the outer galaxy, it's similar like this. And we found that in the outer region, seems this unresolved contribution can indeed, if we add this unresolved source contribution, we can reproduce the data, the measurement in the outer region. But in the inner region, we're still short for this measured flux. I think this even if we add the unresolved contribution, this total flux is still smaller by like 50% of this measured flux. And so there is one issue is that in the first LASSO catalog, it just includes the sources with extension smaller than 2 degrees. So maybe there are some even larger extended sources are not included in this computation, or there are some additional contribution from some unknown mechanism, unknown process. And so one kind of this unknown source population may be this so-called pulsar halo. This pulsar halo, this is in the Hawks discovery in 2017. So they found that for some middle-aged pulsars, there are large extended gamma ray emissions around those pulsars, which may be explained by electron positrons diffuse out around the pulsars and their inverse Compton scattering with radiation field to produce this emission. So such extended halos may be common in the Milky Way. So this is a natural expectation. So if we have many such kind of pulsar halos, and they could form a diffuse component of the gamma ray background, this has been discussed in some previous papers. So here in this work, we actually investigated the possible contribution from the pulsar halos to the diffuse emission, and we based on the ATNF pulsars to select the pulsars with proper age and the proper distances, and to calculate their contribution to the gamma ray emission. Yes, and the top panel shows this total emission from this pulsar catalog. And if we for some of the sources may be bright point like sources which could be detected by the LASSO instrument. So we apply the same mask of this diffuse analysis. So after this mask, we found that the residual sky looks like more like this the emission looks more like a diffuse emission rather than some bright point sources. So that means that this pulsar halo contribution may not be really identified as some individual sources by this detector, and they may indeed contribute as some diffuse emission. And we calculated a spectrum. So this spectrum looks like here for different model assumptions. So add this spectrum to this cosmic ray background, so it can reproduce the measurement relatively well. And this is spatial distribution. The spatial distribution also looks like similar with the measurements. Of course, there are some kind of deviation. I think that basically due to some specific parameters of this pulsars in this regions. So I think this is almost the talk I'm going to present. So here is a short summary. The diffuse emission from 2 regions of the galactic plane. Actually, it covers all the galactic plane in the lasso field of view. Was observed with high significance, and we first detected the diffuse emission in the outer galactic region. And their spectrum is -3. This is consistent with power law index of -3. And the deviation from single power law is not evident. So the current data shows that we don't see some clear spectral structure of this emission. The spatial distribution, the latitude distribution are consistent with gas template, but we found some more complicated structures in the longitude distribution. And the overall flux is higher by a factor of several than the local cosmic ray interaction with the narrow side gas. So that could maybe due to some unresolved sources or some propagation effect. And we show that a pulsar halo model can properly explain this measurements. Okay, that's all. Thank you.
Thank you, Qiang. That was great. Thank you for an excellent talk. Questions? Qi, go ahead.
Hi, Qiang. Can you go back a few slides to the TeV halo masks? Can you elaborate again what's the reason that you identify TeV halos producing diffuse emission when they are masked out? Are these on the right-hand side? Are they models? Okay, they're models. So if you model, okay, you mask out the model.
You mean this page?
Yes, yes.
Yeah, the right panel is the model, prediction.
Okay, based on a diffusion model.
Here, well, so here basically we start with this ATNF pulsars, pulsar catalog, and in this catalog we select the pulsars with the so-called middle age. With there is a range of their age. And for each pulsar, we assume electron spectrum, and again we assume some kind of energy injection in this electron and positrons following this so-called spin down law, and then those particles are then propagate around this pulsars. For this particle propagation, we assumed some like a slow diffusion around those pulsars with typical diffusion coefficient consistent with the like the Geminga case. And yeah, for this Yeah, I think yeah, more or less like that.
So for the electron diffusion, do you take into account the energy dependence, or because you are observing at the similar energy as Hawk, so you just take their diffusion model?
Yeah, I think we should assume that some kind of E to like 1/3 diffusion, energy dependence of diffusion.
Okay, thank you. I have a second question. You showed a spectrum for the when you mentioned the cosmic ray spectrum E, and you mentioned the internal absorption quite a few slides back. So can you, right here, can you comment on what's the target photon field that's doing the gamma-gamma pair production with lots of photons?
I think for this energy range, the target photon is mainly from the CMB.
Okay, thank
Yeah,
you.
because there's optical to infrared absorption in the Milky Way actually is not significant. I think the most significant effect, even from the galactic center, this absorption from the infrared and the optical background is something like 20%. I think that's separation. But if for the same B, it will result in a bigger effect of the absorption.
Thanks, Qiang. So actually, before we go to Evgeny, Paulo has a related question. So Paulo, why don't you ask?
Yeah, no, similar question. So how strong is the evidence for a cutoff or lack of a cutoff at, say, 100 TV? Because as you said, the CMB becomes important. And if there is no cutoff, can you get a useful limit on source distances? Everything must be within 10 kiloparsecs. Have you guys tried that? To use?
Yeah, so currently, I think from this this spectrum, I would say that we actually do not see this very clear cutoff behavior. The reason that we don't see this may be due to that we actually see the contribution from, for example, this background contribution plus or Thomson halo contribution looks like this way. So the sum of these two components gives a power law distribution like this. If we just look at this high energy part of, for example, about 100 TeV here, I think this spectrum maybe I'm not sure, maybe consistent with this curved shape of the gray band. But currently the uncertainty is somehow large.
Okay, because that would be interesting. Yeah. Okay. Yeah.
Yeah, hopefully with like more data we can see some if we see some kind of spectral curvature in this energy range, I think that could be quite interesting.
Okay, thanks.
Yeah.
Thank you. Go ahead, Evgeny, with your question.
I also have two questions. One is about the tentative unresolved sources. If you just take the population of the sources and continue the sources from bright ones, which are resolved to sources which are not very strong, how many of them do you need in this part of the distribution, in the low flux part of the distribution, if you just extrapolate the plot?
Yeah, yeah, basically you can see that here is this extrapolated contribution of this unresolved source population. Basically, I think it shows this part, because the blue is the detected part. We need to subtract this blue parts and basically show this difference between the red and blue. So that is shows like here. This is our inferred unresolved source contribution. I'm not sure if this answers your question.
It's not too many, as I understand, right? You need a factor of 2 more than the number of resolved sources. Am I right?
the number of sources, okay, you can, something like that. But this
Okay.
can be extrapolated to even smaller flags actually.
Yes. And then the question is about the spectrum. You also showed us the spectrum, which is the cumulative spectrum of the unresolved sources. But what about the spectrum of resolved sources? Is it the same or not?
Okay, spectrum of resolved sources. I didn't show that a spectrum. Well, here you may say that this gamma ray, this index of this resolved sources, all these are resolved sources actually. So you will see the index is here, and it's a sum. It's well, it's hard to see this spectrum. And anyway, we and previously we just checked that this how this diffuse emission compared with this total emission. And the total emission seems is somehow even softer than this diffuse emission. The spectrum is even softer. So in that case, we may expect that the contribution of the resolved sources has a spectrum softer than this diffuse emission. I think it's something like here. You can see my mouse.
I see.
Yes, something like this.
Yeah. And then the second question is about the predictions, what you call the toy model. It seems that it should include some kind of estimate for the model uncertainty. But can you comment on how we can get any idea of the model uncertainty? Because the model is really simple. The real situation could be much more complicated. Is there a way to really estimate the model uncertainty? Yes, I see the gray region which is expected to present this uncertainty, but I'm not sure that it's that precise. Can you comment on that?
Yeah, I think you are right. So currently the model uncertainty actually is large. So here this band just include a part of the uncertainty is from this cosmic ray flux measurement at particularly at this high energy range. So we see that this even the local cosmic ray flux, the different experiments have quite some large difference of the measurements. So this will give this uncertainty here. But the further uncertainty is that for example, for the gas column distribution, I guess there should be still like at least a factor of 2 uncertainties. I think in some parts it may be even larger. This uncertainty may not be uniform in the galaxy. And the third uncertainty comes from the cosmic ray distribution. It's we know that there are some models to predict that this cosmic ray spatial distribution is is very non-uniform. For example, I think this French group by Dimitri Semikos and their colleagues, they show that this anisotropic diffusion model, it shows that the cosmic ray distribution in the galaxy is actually is very local. For example, in some places the cosmic ray intensity is quite high, and in some places it may be quite low. So in that case, I think this will also result in big uncertainties. If we consider all these uncertainties, I would expect that the uncertainties is like a factor of 5 or even 10 maybe.
Yeah, I see. So in principle, if you do something more realistic, then it's not really in contradiction with the data. Do I understand it correctly? There is no contradiction between the data and the model if you try to take into account all that certainty. Not at this moment.
Yes. So, well, I think the uncertainty is that is about the absolute flux. I think the uncertainty is somehow high. However, we can also get some constraints or some information from the spectral shape. I think so. Currently, this
Yes.
the measurements shows that the spectrum actually is not as simple as the direct prediction from the cosmic ray interaction. Yeah, for the cosmic ray
Yes.
interaction, we see that we have this local measure spectrum shape looks like this, and the prediction is even there is some spatial distribution of the cosmic ray intensities, but we would expect the spectrum shape is more or less looks like this. So in this case, I think it may not be easy to just tune this cosmic ray distribution to reproduce the data. This may be some constraints from the spectrum, I think.
Thank you.
Thank you. Let's take a question from Kaya. Go ahead, Kaya.
Hi, Qiang. Thanks for the interesting talk. I missed the first 15 minutes, but I'm just wondering, all these lasso sources don't have good distance measurements, right? So I'm wondering how the unknown source distances can affect your, modeling and then matching with the data here.
Oh, yeah, we for most of the sources, we actually don't have the distance information. But this the lack of distance information actually I think does not affect this analysis, because for example for this analysis, if there is a source there, we just mask out this region. We do not consider the regions there. So this source distance is not a matter for the analysis. And this is for the model. The model part is again is not relevant to the source distance. I think for this model calculation, it basically use we have this, for example, the toy model basically just use the local cosmic ray spectrum times the gas column density to get this prediction. And even for this like this Galactic model, we assumed some kind of spatial distribution and to calculate the diffuse cosmic ray distribution in the galaxy. So I think the source distance is not an issue here.
But the gas column density data is assuming, maybe it's everything including in the line of sight, but your lasso sources could be actually closer by, right? In that case, the product of gas density and then can I see that slide again? Yeah, local cosmic ray times gas column. I mean, could it be lower or something? And then does it affect your Gallup predictions?
Oh, well, so yeah, maybe. So you mean if there is some kind of narrow sight contamination, right? So for some narrow sight, there could be some source contribution there, and yes, if we cannot resolve such kind of sources, for example, if there is a faint source in a line of sight, that faint source will contribute to the diffuse flux we observed. Yeah, that's true.
Okay,
but
yeah,
if the source is bright enough, we can just identify it and we subtract it.
Okay, and then my second question basically riding on what Qi and then Paul are asking. So what about comparing with the Fermi results? And the other question is, can using IACT source, data for the estimating unresolved point sources, is that something helpful for refining your analysis?
Yeah, so related to that, let me just add to Kaya's question, because I had a similar question. Maybe you can answer them together, because I think what you said, correct me if I'm wrong, that the data access compared to the model is mostly in the 10 GeV to 10 TeV range. Is that correct?
Yes.
So that's
Yes.
kind of like the Fermi sort of range and the IACT range. So then I guess Kaya's question and Chi's question what do you see? How does it compare with Fermi, for example, or what the IACT see?
Okay, so yeah, basically here is the Fermi results. So this Fermi result is reanalyzed by actually by us in this paper. The reanalysis is mainly to first we subtract this again this resolved sources in the Fermi catalog, and then we apply the same mask as they came to it as the LASSO data. So basically, this Fermi results and the LASSO results are from the same sky regime. And we compared with this prediction. Yeah, we found this excess is mainly in this energy range. So yeah, it looks like that this spectrum is harder than in the Fermi range is harder than the prediction, and this could be due to some like this unresolved source contribution. I remember that in the Fermi's paper in 2012, they also found similar excess in the galactic plane, region. So above this like a few GeV energies, and in that paper they again they expect that there could be some unresolved source contribution from this this contribution to this excess diffuse emission. So your question is about the IACT results. That means by HEISS?
Yeah, I think Hess has some publication of the spectrum, right?
No spectrum. I think in the HEISS paper they just show some here shows the this is the HEISS results. Basically, they show some flags. I think this is some integral flags in energy range and versus the longitude or latitude of the this is for latitude distribution. This is for longitude distribution, and their results shows that yes, there could be some again some excess compared with this model prediction. However, I would think that in the HEISS analysis, this I think this source contamination may be even stronger. Because first, if you look at this, this region is very close to the galactic plane, and for most of these sources, the HEISS, the masked region is very small, very limited. From our current knowledge, we found that most of these sources actually is more extended than what HEISS and other IACT observed. That's maybe due to that for this small field of view observation, the background is somehow overestimated and result in some like a smaller extension of this sources. So I guess in this case, this source contamination may be even stronger.
Thank you. Any questions? Any other questions?
I think a follow-up on that. So Paulo asked about the neutrino spectrum. Can you go back to that slide where you show Fermi and LASSO and Tibet AS gamma spectrum? So the LASSO spectrum is much lower than the Tibet AS gamma, right? I think the Galactic AS gamma spectrum is consistent with the ice cube galactic neutrino spectrum, but now LASSO is much lower. Is that in tension with the ice cube galactic neutrino spectrum?
Oh, yeah, I think this is a good question. So yeah, actually I have a backup slide to try to address your question here. Yeah, this one. Yeah, first we use this the LASSO data and we do the same with S gamma's mask. So S gamma's mask is basically 0.5 degree around each sources. So this is the S gamma's mask. So after the mask, we found that there are some sources even to 13 or 14 sigma axis. So that means that there are strong sources are not excluded in this analysis. Nevertheless, we use this analysis, we get the spectrum look like here. So it seems, if we consider that the error bar is somehow large by AS gamma, we could say that these two are somehow consistent with each other. And this result is higher by like a factor of 2 than what we finally reported in our analysis. So basically, this factor of 2, I think, comes from this unsubtracted source contribution. The argument is that here this plot shows the this radius distribution, the extension distribution of the last sources. We see that this is so-called R39. So basically, this is 1 sigma radius of the two-dimensional Gaussian source distribution. So we see that actually quite some sources have extension larger than this R39. And even for, this is a 0.5 degree. And even for this, those sources below this, smaller than this 0.5 degree, we see that this is 40%, 39% containment of the signal. So that means quite some emission of these sources cannot be subtracted if we just use this 0.5 degree mask. So I think this could explain this why this flux is like higher by a factor 2 than our final results. And as for the comparison with the ice cube, I would say that the ice cube actually do not subtract any sources. They just give this total emission. So that include the diffuse emission and the sources, right? And there are hadronic sources in their field of view. Their contribution may also be included. So maybe, for example, this kind of sources, this kind of part, they have high gamma ray emission. They may also contribute to the ice cube neutrinos.
Yeah, thank you. Any other last questions? Anyone else?
Can I ask one last question? So, Qiang, can you go back to the TV halo slide? It's nice to see you can explain the data. Where?
This one?
Yeah. So yeah, that's right. I'm just wondering if if you can predict the local positron flux and spectra, and if it's matching with the measurement or not, based on this model.
Yeah. Sorry. Can you repeat your question?
Yes, I'm wondering if you take this pulsar halo, model, and can you predict the local positron flux and spectrum, and how it compares with the measurement of positrons?
Our point source, the spectrum, I think it looks like a hair. This is the predicted spectrum from the pulsar halo population, actually.
I think Kaya's asking about it. If you go back one more slide, 20. So if you look at the right-hand side, I think what you're doing is you take the ATNF pulsar catalog, because in the gamma ray range, you don't see that. I mean, there are only a handful of sources that have been identified as halos, but you're making a prediction from the ATNF pulsar catalog, and then making a prediction of if there were halos that we are not seeing in gamma rays, but they could be contributing to the diffuse, if I understand the question, diffuse emission, which is on your next page in your model, but then you make predictions on the individual.
Okay, I see.
I'm actually going ahead and asking. Yeah,
Yeah.
asking about if your model can predict the positrons propagation, and then how it compares with the local positron flux and excess.
Yeah, yeah, I think so. Yeah, for example, if we say that this panel, this is without any mask, we say there could be some kind of point source from this prediction, right? And some of the sources may actually, yes. So yes, we say that some regions actually is overlap with this mask region. So that means for this regions, we do observe some sources there, but whether those sources are just the emission from those pulsar halos, I think that may need some further investigation. I think so. Yeah, we can predict the this individual pulsar halos that may be detected by LASO. I think so.
Okay, well, thank you very much. I think we'll stop here.
Okay, thank
Again,
you,
for a
thank
great
you.
talk, and I would, we would appreciate getting your PDF slides if you could email them to me, and
Sure,
I
sure.
can print it on our website. Okay. And
Okay.
thank you everyone for joining. It was really great. Bye bye. Have a great day.
Thank you, thank you.